Hello and welcome to our talk on our paper entitled Risk-Aware and Multi-Objective Reinforcement Learning with Distributional Monte Carlo Research. This paper is by Conor, Mathieu, Diederik, Enda and Patrick. So firstly, let me just introduce a few concepts and ideas. So in certain scenarios, the utility of a user is derived from a single execution of a policy. What that means is there are certain scenarios where you may only have one opportunity to execute your policy. For example, in a medical setting, a patient who is ill may only have one opportunity to treat their illness. So in such scenarios, making decisions based on the expected value is not sufficient. And our kind of key insight is that we need a distribution over the returns instead to make decisions. So we present a distributional Monte Carlo research algorithm, which learns a distribution over the returns of different policy executions. And we show that this distributional Monte Carlo research can learn good policies under risk-aware and SER problem domains and achieve state-of-the-art performance in ESR settings. So these are a few concepts that are kind of crucial to our algorithm. So we have multi-objective reinforcement learning, and in multi-objective reinforcement learning, two optimality criteria exist. We have the scalarized expected returns and the expected scalarized returns. Then we're going to present a ESR-specific algorithm known as expected utility policy gradient. Then we will look into Bootstrap Thompson sampling and Monte Carlo tree search, both of which are crucial to our distributional Monte Carlo tree search algorithm. So what is multi-objective reinforcement learning? Essentially, it's an extension of single objective RL, except we focus on decision problems with multiple objectives. And instead of a Markov decision process, we use a multi-objective Markov decision process where R, or the returns or the rewards, are vectors, where R is an n-dimensional vector and n is the number of objectives. More methods can be single policy or multi-policy. In this particular paper, we focus on single policy methods where we learn a single optimal policy that optimizes the user's utility function, where the user's utility function, of course, is the user's preferences over objectives. And various different scenarios also exist in multi-objective RL, depending on the availability of a user's utility function, but we're not going to go into those today as we kind of just focus on single policy methods. And as I already mentioned, two optimality criteria exist, SER and ESR. So for the scalarized expected returns, it's the most commonly used optimality criterion in multi-objective RL. And that means that the utility of a user is derived from multiple executions of a policy. And that means that the user has multiple opportunities to execute their policy. To compute SER, basically you first compute the expected reward, and then you apply the utility function. And of course, the expected reward in this case is a vector. For the expected scalarized returns, this has largely been ignored actually by the multi-objective RL community. And as I already mentioned, this scenario, the utility function or the utility of a user is derived from a single execution of a policy. So that means you only get to execute your policy once or a few times. In order to calculate the ESR value or the ESR criterion, you apply the utility function to the return vector first, and then you compute the expected utility based on that. So as you'll see here, the utility function is applied to the return vector or the reward vector, and then the expectation is computed. So for linear utility functions, the policies learned under the ESR and the SER criterion are actually the same. There's no distinction between the two. And actually, we can use single objective methods to actually learn optimal policies for linear utility functions. However, for nonlinear utility functions, the policies learned under the ESR and SER criterion are different and can be significantly different. And this has a major impact in multi-objective RL, because if you are using an SER algorithm and really your policy should be learned for an ESR scenario, then you're going to learn a suboptimal policy, and that's going to have implications. And we need strictly multi-objective methods for this, for nonlinear utility functions. That's a very important point as well to make. And I guess overall, really, the lack of understanding or research into the ESR criterion really is problematic because the only real distinction is with nonlinear utility functions, and the lack of research into this area means that the real-world applicability is limited for multi-objective ORL, because in the real world, utility functions can be nonlinear. So nonlinear utility functions also do not distribute across the sums of the immediate and future returns. So as you can see from this equation, that's problematic because that invalidates the Bellman equation for nonlinear utility functions. So that kind of really means that a lot of ORL algorithms are unusable in scenarios, in multi-objective ORL, in scenarios where the utility function is nonlinear. So therefore, we need new methods to be formulated that can both handle the ESR criterion and nonlinear utility functions. So this kind of brings me to the next topic, is an algorithm that can optimize for both nonlinear utility functions and for the ESR criterion, and that's expected utility policy gradient. So the main finding of this paper is that to learn optimal policies under the ESR criterion, the accrued and future returns must be taken into consideration. And the EUPG then calculates the accrued returns, as we can see here, RT minus. And to calculate the future returns, we can see that EUPG uses the sum of rewards received from time step t to some terminal time step n. And we denote that by RT plus. And then to kind of get the utility then in this scenario, we just simply apply the utility function to the cumulative returns, which is the sum of the accrued and future returns, RT. And you just apply the utility function to this return vector, and we get a scalar utility that we can then optimize. And this learns a policy then for the expected scalarized returns criterion. Now, moving on to kind of a topic that's very important to our distributional Monte Carlo tree search algorithm is Bootstrap Thompson sampling. So distributional Monte Carlo tree search aims to maintain a posterior at each node in the search tree. However, this is not always possible. And basically, in cases where this is not possible, it's important that we can somehow approximate a posterior. And we found that Bootstrap Thompson sampling can do just that and do it very, very well. Initially, BTS was proposed in a multi-arm bandit setting where each arm, I, has a Bootstrap distribution that contains a number of Bootstrap replicates. And when we say a number of Bootstrap replicates, we say a parameter J is a set of Bootstrap replicates and creates the value that you set J to creates a set of a certain size that is full of these replicates. And generally, a small J or a small value for J will make your Bootstrap Thompson sampling algorithm greedy, while a larger value will increase exploration. But as you increase your J value, you increase the size of the set and increase the number of Bootstrap replicates, and thus, as you'll see in a moment, updating each distribution becomes a bit computationally expensive in a sequential decision-making problem. Not so much in a multi-arm bandit setting, but in the sequential decision-making problem, you will definitely notice that. So each Bootstrap replicate contains two parameters, alpha and beta, where alpha divided by beta is an observation. So to determine then an optimal action for each arm, the Bootstrap distribution is sampled. And the arm with the maximum returned observation is then executed. So once we've executed an action or pulled an arm in a multi-arm bandit setting, we must update that arm. And we simply just update the arm with the return that we received. BTS uses a random reweighting strategy to update the distributions. This is actually can be done online and it's computationally cheap, and it's a good method. So for arm I, a Bernoulli bandit is sampled for each Bootstrap replicate. And if the Bernoulli returns a 1, then the Bootstrap replicate is updated. And simply to update it, you just add the alpha and the returns, and you add 1 to the beta value. And that's how you update your distribution. So next topic that's kind of crucial or very important to our algorithm is Monte Carlo tree search. Monte Carlo tree search is, a very popular algorithm, and it uses a heuristic tree search to solve decision problems and has had great success with problems like Go. I think everybody's very familiar with Monte Carlo tree search in the RL community, but I'll go into some detail here. Monte Carlo tree search, it builds a search tree of nodes where each node has a child per action. And there are two phases, the learning phase and the execution phase. And I think everybody's probably fairly familiar with the steps in the learning phase, but I'll go through them anyway. During the learning phase, the agent builds a search tree using the following 4 steps: selection, expansion, simulation, backpropagation. And selection is exactly what it says. The agent will select a node to traverse to, and it will traverse to that node. And when it's at that node, if the node is a leaf node or is a candidate for expansion, the agent will add a child node to that node. And once a new node is created, we then simulate from that node to a terminal state. And those are random Monte Carlo simulations. And then once we reach terminal state, the agent will receive some sort of a reward, and that reward then will be back propagated back up to the point where the agent started. And then simply at the execution phase, the agent just selects a child node which to traverse to. So that will be a node that maximizes the heuristic that the Monte Carlo tree search algorithm is using. And that brings us on to our algorithm, distributional Monte Carlo tree search. So as we've already kind of stated in the introduction and kind of throughout, like the majority of multi-objective RL and RL research focuses on learning a policy that maximizes the expected returns. But our kind of key insight here is that the expected returns cannot account for the range of positive or adverse outcomes a decision may have. And making a decision on the expected returns, we can say really does not provide the agent with sufficient critical information to understand the exact implications of taking an action. And this really is crucial for multi-objective RL under the ESR criterion and for risk-aware reinforcement learning. And especially in scenarios where the policy may only be executed once, which basically is the ESR criterion. So we propose a distributional Monte Carlo tree search algorithm that learns a posterior distribution of the returns. Not only that, but DMCTS can learn optimal policies for nonlinear utility functions for risk-aware RL and for the ESR criterion. It's important to note as well that we can also optimize for the SER criterion. As I'll explain later, but this DMCTS is kind of a hybrid algorithm in the sense that we can do both. We can, with a minor change to the algorithm itself, we can actually optimize for ESR and for SER, not at the same time, obviously, but for different problem domains, and we'll evaluate that later also. So it's a kind of an interesting take that we can do both. It's important to also note that DMCTS is a single policy algorithm and relies on the utility function of the user to be known at the time of learning or planning. So we won't be learning any coverage sets or Pareto fronts or anything like that. This is just, we'll learn a single optimal policy for the given utility function. So similarly to Monte Carlo tree search, DMCTS has a learning phase and an execution phase. And we use the same steps during the learning phase of selection, expansion, simulation, backpropagation, and that. Except we aim to build a expected max tree. So an expected max tree uses both chance and decision nodes. Each decision node represents a state, action, and reward of an MOMDP and has a child chance node per action. So at each chance node, the environment is sampled, and if an unseen reward is generated, a new child decision node is created. We maintain a distribution over the utility of the returns at each node in place of the expected value, which is traditionally used by most multi-objective RL and RL methods, with the exception of some. Obviously, distributional RL has become more popular recently. As I mentioned already here, it's an algorithm that's defined for ESR, but we can also do SER also. And important to note, we maintain a posterior distribution over the utility returns at each node. So before we get into the details of how we're going to actually update the distribution, it's important how we can kind of compute the distribution and also still satisfy the ESR criterion. So as I mentioned previously, we have to do the accrued and the future returns, and that's where Monte Carlo tree search fits in, or into kind of the why we picked that underlying algorithm to use is because we can execute a policy all the way to the end and then bring that kind of policy execution back and back propagate that back up. So that makes it perfect for computing the future returns. And the tree structure, the underlying tree structure of the algorithm, it makes it easier to compute the accrued returns also. So as I said before, the accrued returns is the sum of the rewards received when traversing the search tree during the learning phase. And the future returns are calculated then, and they of course are the future returns are the sum of the rewards received from traversing the search tree during the Monte Carlo simulations. So if you look at the left hand side, you can see how the RT to the minus is computed, and that's just simply you start at a state S0, you take action A0, you take maybe a few more actions, and eventually you arrive at a state ST, and that is a state then that needs to be expanded, or a node that needs to be expanded, excuse me. And basically you can take RT to the minus then to be the sum of all the returns you received, or all the rewards you received going from S0 to ST. So then you essentially, your algorithm says that it's time to expand. You expand your tree, your node, you create a new node, and then you do a Monte Carlo simulation. So basically your future returns then are the rewards received from ST going to all the way to STN during a Monte Carlo simulation. And basically we back propagate then from there. So basically at ST0, we can compute both RT plus and RT minus, ST, sorry. So once the future returns have been calculated and the simulation phase is complete, the cumulative returns RT are calculated. And that's just the sum of RT minus plus RT plus. The utility function is then applied to the cumulative returns, giving us a scalar value now. So we've applied the utility function to our return vector RT, and now we have a scalar value. So the utility function of the cumulative returns is then back propagated to each node visited during the learning phase, and we can back propagate that then from ST all the way to S0. And it's important to note that we update the distribution during the back propagation phase. So at each node, we update the distribution as we back propagate. So we're just kind of giving you an overview here of the process of the algorithm when it calculates the accrued and future returns and how it actually computes the utility. But the reason we apply the utility function here is to ensure that we satisfy the ESR criterion. So during the back propagation phase, the distribution at each node is updated. As I said already, we aim to maintain a posterior distribution, but this is not always possible, and this is where the Bootstrap Thompson sampling comes in. Instead, we maintain a Bootstrap distribution at each decision node. Algorithm 1 on the next slide shows how the Bootstrap distribution at each node is updated for the ESR criterion, and that happens again at the back propagation phase. And then it's important to note that on the initialization of a new node, we set alpha and beta for that node are set to n, and that's for each Bootstrap replicate. Again, where j is a hyperparameter to be tuned, which controls the exploration and exploitation, as I've already mentioned. And again, here we'll see that low j can BTS can become greedy, high j will increase exploration, but at a computational cost. And it can be quite costly, especially in a sequential decision-making process when you're doing so many updates of a search tree as you go from state to state. It can be computationally expensive. So there's a sweet spot there where you get a really good exploration exploitation trade-off that isn't costly to the algorithm, and it can run quite quickly. So we can see here an DMCTS, and this is just the ESR algorithm, which is algorithm 1. And we can just say we get the cumulative returns, and we just apply the utility function here when we're updating the distribution, which is similar to what we saw back 2 slides ago. And then to traverse the search tree during learning, the agent resamples the Bootstrap, the Bootstrap distribution. And this algorithm below, algorithm 2, outlines how the agent selects an action to execute during the learning phase. And basically, we just retrieve we sample uniformly, randomly from the Bootstrap distribution or from the Bootstrap replicates, and we retrieve the parameters of what we get back. So that'll be alpha ij and beta ij. And then we just take, they're both scalars, so we'll just compute the observation, which is alpha ij divided by beta ij, and then just take the node which returns the maximum of those, and we'll traverse then to the node that returns the maximum. Yep, and then of course using algorithm 1 and algorithm 2 ensures that we optimize under the ESR criterion. Since the following is true, alpha ij divided by beta ij is a kind of equivalent or an approximation of the expectation of the utility of the RT minus plus RT plus, which it is. And as we can see from below, that satisfies the ESR criterion. And then at execution time, we simply select the overall maximizing action by averaging over all the acquired data. So I'll just briefly talk about how we can do the SER criterion. Again, it's a few minor changes. We initialize alpha to be a vector, where vector is just full of ones for the number of objectives we will be returning. So we will say it's an n-dimensional vector, or as we use O to denote how many objectives are in the vector here. And then we just keep beta to be the same, of 1. And then basically it's just a similar update, except for alpha is now a vector. We just add RT as a vector to alpha as a vector. And that's basically it. There's no scalar involved here. It's just two vectors being added together, and beta is just the same. And the next slide will show how the distribution is updated. And the distribution is updated very similar to how it's done in the SER or ESR criterion, except for, as you can see, after the Bernoulli, where the alpha ij is equal to alpha ij plus RT. And this is just what we saw on the last slide. It's just two vectors being summed together. And then at decision time, this is where we apply the utility function. And we apply the utility function to the alpha ij to the observation, the alpha ij divided by the beta ij, and that then satisfies the SER criterion as we saw earlier. That's the expectation, the utility function applied to an expectation. And we can see from algorithm 4 that's what we use, and you can see there on the max child is equal to argmax iu of alpha ij divided by beta ij, and that alone satisfies the SER criterion. So you can see how with a very small slight change we can do both SER and ESR, which is really novel and really great to be able to switch between the two, and we can do both linear and non-linear utility functions. So for experimentation, we evaluate our algorithm on a risk-aware MDP, which is a single objective under the ESR criterion. We do dangerous deep sea treasure, which is multi-objective under the SER criterion. And then we have a renewable energy problem, and that is ESR as well, and multi-objective. And then we have Fishwood, which is ESR and multi-objective also. So the risk-aware MDP is a single objective MDP proposed by Shen et al. The agent must choose from a number of stocks to invest a monetary amount. And the goal really is just to avoid losing money. Every time you invest, there's a certain chance of losing and there's a certain chance of winning. And the goal here is to maximize the following utility function with, yep. And we can see here in this figure that our algorithm does quite well. After about 400 episodes, we converge to the optimal policy. And compared to Q-learning, we do really well. Q-learning struggles to learn any meaningful policy. And yeah, so this is kind of, it shows also that our algorithm can also be used in single objective settings, as long as the utility function, of course, is available. But I imagine if we were to do it on any other single objective setting, it would work just fine. Then we use dangerous deep sea treasure. And dangerous deep sea treasure is a kind of a variation of a multi-objective RL environment called deep sea treasure. The goals here is we've added danger into the as an objective, where certain states there is a high level of danger, and you can the agent can end up taking damage, and if the agent receives enough damage, it will actually crash the submarine, and the episode will end. So the goal is obviously to avoid that. So we use a nonlinear utility function where we have a target vector, and we set the target vector to one of the policies on the Pareto front. And basically, if the algorithm can recover the target vector, then it can learn that policy. So that's what the utility function does. It maximizes. It allows us to achieve, achieve certain vectors with that are on the Pareto front if they're known, if we can reach them, of course. And this is just a kind of a general overview of what the state space looks like. We have the areas in kind of light red are kind of danger zones where you may or may not get attacked, and then the areas in darker red are where there's almost certainty of getting attacked, or you will actually be killed for entering those states. Excuse me, your submarine will take damage and crash. And we can see here that let's go back, and if we look at here, we actually set the policy to recover the treasure of 50, which is on the Pareto front here. And you can see here that DMCTS learns the policy and retrieves that vector almost immediately, very, very quickly, while Q-learning struggles to achieve any kind of decent policy. It does okay, but doesn't learn anything anywhere near in the realm of our algorithm. I'm going to quickly go through this slide. Basically, we use a renewable energy reformulation of another environment introduced by Patrick Mannion et al. And basically, the power demand for a town must be met over a 24-hour period. There are 9 fossil fuel generators and 1 generated by renewable energy. The renewable energy generator is, I suppose, can be the output by that is determined by the weather, and unfortunately there is a storm coming into this town, and the weather will be unpredictable. So there's obviously varying different probabilities that we'll have good weather or bad weather, which will allow us to produce or stop our production. And the goal of the agent is to control one of the fossil fuel generators and minimize the penalty violations, the cost and emissions of running that generator. And we optimize this for the ESR criterion, and we compare DMCTS against EU-PG, as we mentioned earlier, C51, which is a distributional ORL algorithm, and Q-learning. And we can see here that DMCTS outperforms all of them. Q-learning does quite well, EU-PG does quite well, but C51 doesn't perform very well. But overall, we achieve quite a good performance in this environment. And finally, we compare against Fishwood. And Fishwood is an ESR benchmark proposed by Roijers et al. Fishwood has 2 states, in the wood or at the river, and 2 actions: to catch a fish when you're at the river and to obtain wood when in the woods. And at the river, the agent has a 0.5 chance of catching a fish, and in the woods, the agent has a 0.65 chance of obtaining wood. So for every fish caught, 2 pieces of wood are required to cook the fish, and that's the utility function we're aiming to maximize. And again, we use the same algorithms from the previous experiment, UPG, C51, and Q-learning. And so previously to this, UPG had the state-of-the-art results in this problem domain, so we can see here that DMCTS clearly beats it and beats all the other algorithms. Again, C51 and Q-learning don't really learn anything meaningful, whereas UPG, which was the previous state-of-the-art, learned something quite a good policy, whereas DMCTS converges to the optimal policy and achieves state-of-the-art results. So in conclusion, we can say that DMCTS is able to learn good policies in risk-aware and SER settings. DMCTS is able to achieve state-of-the-art performance under the ESR criterion. We can also say that to learn optimal policies under the ESR criterion, making decisions based on the expected returns is not sufficient. Instead, a distribution of the expected returns must be used to ensure that the agent has sufficient critical information at decision time. So finally, for some future work, we aim to extend this algorithm to learn the Pareto front in SER settings. And we can say that multi-objective MTTS is able to learn the Pareto front in problem domains with deterministic rewards. We aim to extend our algorithm to be able to learn a set of optimal policies and problem domains with stochastic rewards. So yeah, we really think that this algorithm can be used in both settings to learn optimal policies. So we also hope that we can extend DMCTS also to be able to learn an optimal set of solutions in ESR settings. So hopefully we can kind of create some sort of a hybrid algorithm that can do multi-objective for both SER and ESR with minor changes to the algorithm. And that's kind of the hope. Again, we know that multi-objective MCTS exists, but again, it's limited to deterministic rewards and deterministic settings. So we aim to extend from there. So hopefully, as I said, we'll have some sort of a hybrid algorithm that can do both with very minor changes to the algorithm. And that's it. Thank you all for listening and joining. If you have any questions, my email is at the slide, also on the Slack channel. I would really encourage anybody who's watched this who has any questions, please do reach out on the Slack channel, and we can get kind of a conversation going. I really hope you enjoyed the talk. Unfortunate it's not in person, but maybe next year we'll all be able to get together at ALA and have some more discussions in person. So thank you all.